counting techniques. So we're going to talk about different ways to count things. The first one is called the fundamental counting principles. And all that means is when you have different options and you want to figure out the total ways, you just multiply those options. For example, let's say I have 3 shirts. We'll say I have a red shirt, a green shirt, and a white shirt. And let's say I have 2 pants. We'll say I have a tan and I have black. And the question is, how many different ways can I get ready in the morning, right? How many different combinations could I have for clothes? Well, I could do the red shirt with either tan or black. And then I'm pretty much out of options. I could do the same with the green shirt. I could wear a green shirt with either tan or black. And I can do the same with the white shirt. I could do white and tan and white and black. So I have 6 total possibilities. What the fundamental counting principle says is that instead of laying out all the options, all you have to do is figure out how many options you have for each one. So for shirts, I have 3 options for shirts. For pants, I have 2 options for pants. All you need to do is multiply these 2 things, and I get my 6 possible ways of dressing myself in the morning. So that's the fundamental counting principle. When you have options, you just multiply them together. So let's do an example here. A bike manufacturer makes 5 and 10-speed bikes in 7 different colors and 4 different frame sizes. So I could choose between 2 speeds, 7 colors, and 5 frames. How many different bicycles does the manufacturer make? So, like I said, right, our gear choices, I got 2 gear choices. I have 7 colors. And I have 4 frame choices. So if I'm figuring how many different bikes people make, you just multiply them all together. 2 times 4 is 8. 8 times 7, 56. I hate multiplying those 2 numbers though, but whatever. Get over my fear. So 56 different bikes they sell. And that's the idea. Oh, have this many options, that many options, that many options, multiply them together. Let's do a slightly trickier one. On a quiz, each question on a 5-question multiple choice quiz has answer choices labeled A, B, C, D. How many different ways can a student answer the 5 questions? So here's the thing that's a little tricky about this one. A lot of people want to go, oh, there's 5 answer questions and there's 4 possibilities. So they're going to, oh, you get 20. That's actually not right. Remember how multiple choice quiz works? On question 1, how many different options do you have? I have 4 different options. On question 2, how many different options do you have? You have 4. Question 3, same idea. Question 4, same idea. Right? For each question you have 4 options. You're going to multiply these together. Right? Your questions are the different things you're choosing from. So in question 1 have 4 options, question 2 have 4 options. And you get 4 to the 4th or 256. That's how many ways you can answer this. Right? And that makes sense. You could go A, B, B, B. A, B, A, B, like you could so many different ways, way more than 20. So that's where it gets a little tricky. You gotta think, okay, I'm choosing between the different questions and how many options do I have for each question. Let's do one final example like this. Dane is renting a tuxedo for prom. Once he's shown his jacket, he must choose from 3 types of pants and 6 color vests. How many ways can he select his attire for prom? So he already chose his jacket. So jacket, done. He has 1 option. He chose it. He's happy with that rhinestone jacket. Next, we're going with pants. And this is he 3 types, right? He's going to pick his 3 types of pants. And now he has to choose his vest. And it says he has 6 colors of vests. So you multiply that together, you only get 18 choices. Right? He has 18 different combinations he could wear. Because he picked his jackets, there's only 1 of those, and then 3 pants he could choose from and 6 vests he could choose from. So that's the fundamental counting principle. Next up, factorial, a little blast from the past. So remember, the way factorial works is that if you get a number factorial, like 3 factorial, all you do is multiply that number times all the numbers below it. 3 times 2 times 1, stopping at 1. Once you get to 1, and you get 6. By the way, I want you to note that by definition, 0 factorial equals 1. Mathematically speaking, why does that make sense? Well, factorials have to do with how many permutations, like how many different ways can you rearrange stuff. And the idea is, how many different ways can you rearrange 0 things? Well, there's only 1 way to rearrange 0 things. So that's what makes it 1. I know, a little weird, but that's what we do. So let's talk about this. How many different ways can we rearrange 4 things is what we're generally asking here. So if you have 4 things, A, B, C, D. Factorial says, hey, how many different ways can you arrange that? Could you do A, B, C, D? You could do A, C, B, D. You could do A, D, B, C. You could keep on going. So how many different ways could we arrange this? Well, easy way to do is do a 4 factorial. 4 times 3 times 2 times 1, and that's going to be 6 times 4, which is 24. So 4 factorial is 24, and all that means is how many different ways can you arrange 4 things in order? Same thing with 6, right? So if I go A, B, C, D, E, F, how many different ways can we rearrange those letters? Well, you just do 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. Like we talked about before, this is just 4 factorial, which I figured out was 24. This is 30. 30 times 24 is going to be 0 times all that's 0. 3 times 4 is 12. 3 times 2 is 6. 720. So that's how that works. Now let's do it with the word problem. Permutation and objects. So again, another way to think of factorials is how many different ways can you arrange these 4 things? So here, there are 8 finalists in a band competition. And how many different ways can the bands be ranked if they cannot receive the same ranking? So we have bands, and we're going to try and rank them 8 different ways. Right, so the easiest way to do that, we have 8 things, we're just trying to rank them, 8 factorial. So 8 times 7, blah, 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 blah. Basically, this is 8 times 7 times 6 factorial, which I know is 720. And basically, I'm just going to put all this in my calculator because I can't do it in my head. Here's my calculator. I'm just going to do 8. Let's go 8 factorial. 8, so I can show you how to do it. Math over probability. And down there is the factorial button. So 40,320 ways. So there's a lot of ways to rank those 8 bands. Okay, so that's a basic permutation, how you rearrange these 8 things. Let's look at a more formal version of that, which is this right here. So when I say permutation, we're going to use that as NPR. Remember we did NCR before, we'll talk about that more in a bit. But NPR we're going to say for permutation. Now what makes permutation special? Order matters. As you see me writing right here, order matters. Anytime we're doing something where order matters, it's a permutation. You're like, when does order matter? Well, think of like a race. Probably the most classic example, right? If you're taking a race, like if you're watching the Olympics, it matters who comes first, second, third. First gets gold medal, second gets silver, third gets bronze, right? That matters. So anytime order matters, it's permutation. When does order not matter? We'll talk about that here with combination, but the easiest way to think about that is if you join the group. Right, if I'm picking 3 kids to go get lunch, it doesn't matter if I pick you first, second, or third. As long as you get to come and get lunch, you're happy. And that's not going to happen, by the way. Anyway, the formula for that's this right here. As always, I'll give you the formula for it. All it is a factorial. So let's say I gave you 7p3. According to the formula, that's going to be 7 factorial over 7 minus 3 factorial, which is going to be 7 factorial over 4 factorial. And then you just solve it from there. We talked about that before. You break that down so you get to this number, cancel out, solve it. Now, I'll tell you right now, most of these permutations get big, so most of the time we're just going to use our calculator. Like 7 factorial, like 7p3, we'll just use 7, math, go to probability, and PR right there, order matters, permutation, 3. So 210. How to remember that order matters with P? I just always think about position. If position matters, we use permutation. So let's do an example. How many different ways can 2 students be assigned to 5 tutors if only 1 student is assigned for each tutor? So in this case, order matters. And now here's a trick to order matters. I'm using NPR. Here's a quick trick. The bigger number should always be N. So this is my N. This is my R. Right? This has to be the bigger number. So this is going to be 5p2. You can put in your calculator. I'm actually just use the formula, which is 5 factorial over 5 minus 2 factorial, which is 3 factorial. So I just break that down, I mean 5 times 4 times 3 factorial over 3 factorial, cancel, and I get 20. So again, order matters, NPR, here's the formula for it. Either use the formula or do the calculator. A lot of times we actually just use the calculator because the numbers can get big. We'll do some more examples in a bit. But before we do that, let's go to combination. So combination is the same idea, but it's where order does not matter. Again, best thing I can think of is choosing spots in a group. So if it doesn't matter who gets picked first, second, or third, then it's combination. So The formula for that is NCR. As you see right here, we've used this formula before. That's like the same thing. So if I give you 5C3, it's the same thing as me saying this, right? Remember that notation, which is the same thing as saying 5 factorial over 3 factorial, and then subtract them, 2 factorial. As you can tell by the fact that fraction is a lot bigger, in the bottom there, it's going to be a smaller number. So let's do an example here. How many ways are there to choose 5 cards from a standard deck of 52 playing cards? So in this case, right, you're just like, it's like you're playing poker, you get a hand of 5 cards. It does not matter which card comes first, right? If you get ace first, and then you get a 2, and then you get a 3, then you get another ace, and then you get a 5. You don't have to play in this order. You can rearrange it all you want. It does not matter what comes first. So that's a combination, right? You have a group of cards, combination, right? Because if group, where order does not matter, we're going to use combination. So in this case, I got 52 playing cards, and I got 5 cards. We're going to do NCR here. And again, the bigger number is always N, so 52 is my total. And I'm choosing 5. So 52C5. I can do this lots of ways. I can use a formula. I've shown you can also use Pascal's triangle. But those numbers are huge. I don't want to go 52 rows of Pascal's triangle. I'm just going to use my handy dandy calculator. Come on. 5. And I could get a whole heck of a lot of combinations. There that goes. Here's a couple quick examples. Again, this is just putting your calculator, get a number, or you can do the formula. 2 factorial and then subtract them, 2 factorial. Remember, if you want to simplify this down, all you're going to do is 4 times 3 times 2. I'm going to stop at 2 because that's going to cancel out one of those. The other one is not going to cancel, so you just rewrite it. This reduces with this. You get 6. If you get good at this, you pretty much start doing it in your head. The C one can pretty much do in your head. P is a little different because the numbers get big. Like if I was doing this formula, it's 9 factorial over the difference, 4 factorial, just follow the formula. This is going to be like 9 times 8 times 7 times 6 times 5 times 4 factorial. Right, as you can see, that's going to be a lot bigger. So whatever that has to be. Okay, so that's how you do combination permutation, right? Let's do some examples to tell which one do you have to use. Does order matter? Position, P, or does order not matter? Combination, C. So here we go. Determine whether each situation involves permutation, remember order matters, or combination. Order does not matter. Then solve the problem. So here we go. We go to Baskin Robbins. They have 31 flavors, right? If you choose a bowl with 3 flavors, how many different types of bowl choices are possible? If you choose a cone with 3 flavors, how many different cone choices are possible? So both of these have the same type of question. I know this is my N, it's 31 flavors, it's 31 total flavors, and I know I'm picking 3 flavors. But one of these is permutation, one of these is combination. So let's look at this. We have a bowl. That's my terrible rendition of a bowl. We have 3 flavors. Don't ask. And I have a cone with 3 flavors. And I gotta decide which of these does order matter. And I'll tell you right now, it's because usually easier to tell what matters. It's this one. On this one, if you do like red, blue, green, right? I had to eat this way. I had to eat the red first, then the blue, then the green. I can't eat the green first because if I eat the green, the red and the blue are gonna fall down and start crying, right? It has to go down in this order. So in this case, order matters. So this is 31 P3. That's a huge probability. This one, you have a spoon. You get it, and oh, it's a terrible spoon. You get it any way you want, right? I could eat that one first, or I could eat that one first. I could eat that one first. It doesn't matter, right? They're all equally easy to do. That's combination. So again, order matters, right? I have to eat in this row, otherwise I'm gonna lose my ice cream. Permutation, combination. Let's talk about this with money. 50 people purchase raffle tickets. The 3 winning tickets are selected at random. If each prize is $500, how many different ways can prizes be awarded? So look at what they're saying. There's 50 people. We're going to pick 3 winners. Everybody gets $500 if you win, right? So does it matter if you get picked first, second, or third? No. You get $500 either way. You just want to be selected. So, combination. Doesn't matter if you're first, second, or third. This one, though, 50 people were selected. 50 people were selected for raffle tickets. 3 winning tickets. First prize gets $1,000. Second prize gets $500. Third prize gets $250. So now does it matter if you get picked first, second, or third? Yes. I want to go first. I want the grand. I don't want the third place. So 50 P3. Alright, so order doesn't matter. Order matters. The next couple are a little tricky. So this is the first one. 10 people are waiting standby for a flight to LA. If 4 seats are open, how many seats can be taken? So we know it's going to be 10 and 4, right? So now is it P or C? So here's a little hint. It's all about the details. So in this case, there's 4 seats open. If they would have said something like the first seat is an aisle seat, which was the best seat, by the way. The second seat's a window, second best seat. And the next 2 are in the middle, then it'll be permutation, because it's going to matter. But in this case, they just say, hey, there's 4 seats. All you really know is you want to be one of those 4 seats selected. So 10C4. If they have a little more detail, and like, okay, then there's a difference between these seats, then permutation order will matter. So that's a little shortcut. Next one. Abby is registering at a website and must select a six character password. The password can contain either letters or digits. So let's think about this. How many passwords are possible if characters can be repeated? So what that's saying there is like, let's look how to unlock your phone, right? Let's say I have a 4 character password, and let's say my password is 1, 2, 3, 4. Could I unlock the phone if I do 4, 2, 3, 1? No. Or if I did like 2, 3, 4, 1? No. It has to be this order, right? Order matters when we're talking about passwords. So it can't matter. Order matters. So if no characters can be repeated, so what does that mean? Let's say we have letters and digits. There's 26 letters in the alphabet, and there's 10 digits, right? 0 through 9. So right now I have 36 total. So for A, it says we have a 6 character password. Nothing could be repeated. So that means when, let's say my first letter is A, I had 36 total possibilities. But now I selected A. That means next time I have 1 less. I can't pick A again. No characters can be repeated. So now I have 35 options. Let's say I pick 3. Right? Now 3 is gone. I can't pick A or 3 because nothing can be repeated. Now I only have 34 options. And so on. 33, 32, 31. So I can multiply these all together and get my answer. That's the same thing, by the way, as saying, what do I have? 36 P 6. Right? Because I have 36 options. Order matters, they talked about, and there's only 36 possible characters, and there's only 6 places. And then remember the formula for this? It's 36 factorial over 36 minus 6, 30 factorial. Should be 36 times 35, all the way to 30. And then these will cancel out, and you basically get that. Now let's look at B. How many passwords are possible if all characters letters can be repeated? So they're saying, hey, you picked A, you can pick A again all you want. So in this case, it's going to be 36 times 36 times 36 the whole way. So that's basically going to be 36 to the 6th power. And then look, they have another question. And if the password must contain exactly 1 digit. So I'm saying for one of them, you have to have a digit. So in that case, we only have 10 options. And actually, they say it must contain exactly 1 digit. So there's my 1 digit. The rest can't have a digit. So there's only 26 letters. So 26 times 26, 26, 26, and so on. Which type of password is more secure? This one is. Why? Because that's more combinations. It's 36 times 36 the whole way out. This is 10 and 26, 26. Sounds more secure. You have way more possibilities. Okay, last type of problem in this thing. We'll go on to the next lesson. For Fregoso's lunch, he had the following menu. How many different ways can he eat? So look at this. Now, anytime we do P and C, if you notice, I should probably just explain this better. You're picking a subset, right? I'm picking 4 out of 10. Permutation combination. I'm picking 3 winners out of 50. Permutation combination. Right? I'm picking 3 flavors out of 31. All the subsets, if you're picking a subset, right, a small group out of a bigger group, then it's NPR or NCR. In this case, I don't have a subset. I'm not picking 3 snacks out of a total of snacks. I have choices. And if I have choices spelled correctly, then it's a fundamental counting principle. I'm just going to multiply my choices, right? For a snack, I have 3 options. For my meal, I have 2 main options. And for my drink, I have 4 options. I get 2 times 3 is 6. 6 times 4 is 24 different ways I can choose my meal. By the way, if I wasn't choose my meal, I'd probably want a salad, then a burger, and let's go some lemonade. So that's it for that first part. So let's move on to 05, adding properties. So here we're going to talk about probability, what it means. So probability is the likelihood something's going to happen, right? Probability is a measure of a given event will occur, right? So probability is the likelihood, the odds of something happening. Now, keep this in mind. So if you have a 0 probability, that means it's not going to happen, right? There's no such thing as negative probability. If I say it's going to rain cars outside, that's not going to happen. 0. It's not -2 or anything. 0. And likewise, the max probability is 1. There's no 200% chance of something happening. It makes no sense. 100% chance is the max you're going to get. That means it's going to happen, right? Halfway is 50. It's equal likely both ways. Now there's 2 types of probability. There's theoretical probability, which we're going to talk about first. That's just based on the math. So like when you roll a die, right, there's 6 things. 1, 2, 3, 4. You can get one of those. Odds of rolling an even number, well, there's 3 even numbers. So you have a 3 out of 6 chance. Experimental probability is based on experiments. So let's say you roll 100 die. How many? And then you figure out, oh, based on my 100 die, what's the odds of rolling each different thing? So that's theoretical and experimental. Theoretical, based on mathematics. Experimental, based on an experiment. What they both have in common, the way you find the probability of anything is always the same. It's the probability of the want, like how many times does the want happen, over the total. How many times the total happens. So want over total is the key. If you want to find the probability of anything, I don't care if it's experimental or theoretical, want over total. So let's look at this example here. The graph shows the results of several trials of an experiment in which a single die is rolled. So they rolled die lots of times. What is the experimental probability of rolling a 6? So based on this experiment here, rolling a 6, right? Probability of getting a 6, 1 over total. Well, how many times did it roll a 6? Here's my 6. They rolled it 10 times. Now the total, sadly they didn't tell us how many times they rolled it, so we had to count it ourselves. That looks like 9, 6, 12, 6, 7, 10. If you add all those up, get 50. So you have a 1 in 5 chance, according to the experiment, to give 6. Now look what the question says. What is the theoretical probability of rolling a 6? So based on like mathematics and logic, right? Odds of getting a 6. Like we talked about, there's only 6 possible choices, and there's only 1 6. So you have a 1 in 6 chance. So based on this experiment, you get a 6 every 5 times. Based on mathematical theory, and just like logic, mathematics of that, you get 1 out of 6. Now let's talk about some properties of probabilities. So when 2 events occur, so there's lots of different ways you can do this. And the best way to do this is look at cards. So mutually exclusive means things that they have nothing in common. So I know it's a little funky because you're like thinking exclusive, like, oh, we're exclusive. But mutually exclusive means they're all by themselves. They don't like anybody. They don't share a thing. So mutually, each one is exclusive. So they have nothing in common. Nothing in common. So the best way to think about this is cards. Now, if you guys don't know cards, right, there's hearts, which have 13 cards. There's diamonds, which are 13 cards. These are red, by the way. There's clovers and spades, all of which 13 cards. These are black. Cards go from ace, 2, 3, all the way to 10. Then we have a jack, a queen, and a king. So here, they're saying kings and queens. If I say kings and queens, well, there's only 4 kings, right? There's 1 for each, and there's only 4 queens, 1 for each. They have no cards in common. There's no king that's also a queen in cards. Not mutually exclusive means they have something in common. So if you look at kings and spades, well, there's 4 kings, 1 for each color, and there's 13 spades, all these. But this includes a king also. So they share that king, right? Kings have 4 kings, including a king of spades. And spades have a king of spades. So they have something in common that makes it not mutually exclusive. Now there's formulas for this. When they're mutually exclusive, this is a formula to figure out the probability. So if you want to find the probability of getting a king or a queen, well, odds of getting a king, remember 1 over total. There's 4 kings in a deck, and a total of 52 cards. But if you didn't know, cards, there's 52 total cards. 13 times 4. Probability of getting a queen, same idea, there's only 4 queens and there's 52 total cards. So probability of getting a king or a queen, just add them up. 8 out of 52. Simple enough. What if they have something in common? Then it gets a little trickier. So there's this formula, and I love this formula. Why? Because it always works. That's why I love it so. So we're going to use this formula a lot. So what it says is, hey, what's probability of getting a king? Well, there's 4 kings out of 52. Then it says, what's probability of getting a spade? Well, there's 13 spades out of 52. Now, if you add all this up, we're probably getting a king or a spade, and we'll explain what or means later. What's the odds of me getting a king or a spade? Well, if I added that up, I would get 17 cards. There's not 17 cards here. So what's going on? Well, we're adding the king twice. We're adding the king with the kings, and we're adding that king with the spades. So the way we get rid of that is we subtract off what they have in common. So we're going to subtract off 1 out of 52. And if you add that up, you get 16 out of 52. And that's the odds of getting a king or a spade. 16 out of 52, because that's how many cards that are both kings or spades. Over here, you can use the same formula. If I use this formula over there, I'll subtract off the and. Notice that they have nothing in common. That says to me 0. So it still works. I love this formula. It always works. This formula only works with mutually exclusive. This formula always works. So we're going to use this one a lot. So we're going to keep that formula in mind. Again, another formula we'll give you. So let's do some examples here. Determine whether the events are mutually exclusive, which means they have nothing in common, or not mutually exclusive. Then find the probability. Keisha has a stack of 8 baseball cards, 5 basketball cards, and 6 hockey cards. If she selects a card at random from the stack, what's the probability that the card is a baseball or hockey? She wants to know what's the odds of getting baseball or hockey. So first thing I'm going to do is write down my favorite formula. When I say that, I mean stats, not of all formulas. So I'm going to write this down. Because again, this formula always works. Now this U here, I should have explained this earlier, that means or. So I can have this or that. Always think about it like food. If I said, oh, you're going to a restaurant, can you bring back burgers or fries? I'll be happy with either one. Burgers or fries. Either one of them good. This symbol means and. And you need both. That's what they have in common. If I said I want to come back with burgers and fries, and you only come back with burger, I'm gonna be like, what the heck? I wanted burgers and fries, right? So and you need both, or just one or the other. I quickly erase the A and B and put it baseball and hockey to make it a little easier. So look, let's go back to the problem. If she selects a card at random, what's probably that it is a baseball or hockey card. So baseball or hockey, we should have with either one. So that's what we're trying to find. So based on this formula, what's the probability of getting a baseball card? And remember the way we do that? It's want. How many baseball cards do I want? There's 8 of them. Over the total. So there's 8 baseball, there's 5 basketball, and there's 6 hockey. That's 11 plus 8. There's 19 cards total. So it's going to be 8 out of 19 chance of getting a baseball card. Odds of getting a hockey card? Well, there's only 6 hockey cards, so 6 out of 19. Now here's what we talk about, is it mutually exclusive or not? Because there a card that's both baseball and hockey? There's not. I can't get a baseball and hockey card. There's no card that has both sports. So this is 0, which means it's mutually exclusive. They have nothing in common. So if I add those up, this should have been 19. I don't know why I put 12. And I get 14 out of 19. Next one. Suppose that 1,400 students, there are 1,400 students, 550 take Spanish, 700 take bio, and 400 take both. What's the probability that students selected at random take Spanish or biology? So I'm going to use my same formula I love. Spanish or, that's an or symbol, biology equals probability of Spanish plus probability of bio minus probability of Spanish and bio. Now in this case, right, probability of Spanish is 550 over the total 1,400. Probability of bio is 700 over 1400. And they told me, hey, 400 take both of them. So subtract off what they have in common. These take both Spanish and bio. And if you do that, do a little math, you're going to get 150, 850 over 1400. That's fine. Or if you want to reduce it, 85 over 140. If you want to reduce it, you're a better person than me. So that's those two. Last couple before we're done. Determine whether the events are mutually exclusive or not, then find the probability. So 2 die are rolled. Sum of 10 or doubles. So think about how you get a sum of 10. So that could be, if we're rolling die, remember die are 1, 2, 3, 4, 5, 6. We're going to roll 2 of them. So let me write it again so we get a little thing we work with. So I could get a 10 by doing 5 and 5. I could do a 10 by doing 4 and 6. I could also do 6 and 4. And I believe that's it. Only ways I could get 10. Doubles, so there's 3 ways to get 10. Doubles, how do I get doubles? Well, 1, 1, 2, 2. There's 6 ways to get doubles. Now here's the thing. If we're rolling 2 die, what's the total? Let's go back to our fundamental counting principle. When I roll 1 die, there's 6 options. When I roll another die, there's 6 options. So I have 36 total options. Now, let's do my favorite formula. I want to get a sum of 10, or, it says sum 10, or doubles. I'll put 10 or doubles. So that equals probability of getting a 10, plus probability of getting doubles, minus what they have in common. Probability of 10 and doubles. Probability of getting a 10, remember we figured out there's only 3 ways to get a 10. So 3 out of 36, right? 36 possible ways, because if I wrote, there's 6 ways to get this die, there's 6 ways to get that die. 6 times 6 is 36 total different ways. Probably getting doubles. Well, there's 6 doubles, right? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So 6 out of 36. Now, do they have anything in common? Let's look at it. The only ways I could get 10 were 5, 5, 4, 6, 6, 4. That's a double, right? So there's one thing in common. 36. I don't know why I wrote that. And there you go. So they're not mutually exclusive because they have something in common. So not mutually exclusive. And the probability would be 3 plus 6 is 9. 9 minus 1 is 8. So you have an 8 out of 36 chance of either getting a sum of 10 or a double. So let's look at this one. Sum of 6 or 7. How do we get a sum of 6? Well, 3, 3. 2, 4. I can also get 4, 2. 1, 5. And 5, 1. I don't think I missed anything. I think that's the only ways. I'm getting a sum of 7. 3, 4. 4, 3. 2, 5. 5, 2. Now if you notice, they have nothing in common. So I can do the exact same formula. This would be 5 out of 36. This would be 4 out of 36. And then they have nothing in common. So 0 out of 36. So these are mutually exclusive. I just do 5 plus 7 or whatever I got and add them up. How about this one? Sum less than 3. It's like, remember, it can't be 3, it has to be less than 3. There's actually only one way to get something less than 3. 1 and 1. So only one way to get a sum less than 3. Right? Actually, yeah. Right, because if I do 2 and 1, I get 3, and I have to be less than 3. A sum greater than 10. Well, I could do 5, 6. 6, 5, I get to be 11, or I could do 6, 6. So there's 3 ways to get a number greater than 10. So again, if we do our favorite formula, minus what they have in common, I'm running space. Right, probably getting it less than 3 is only 1 out of 36. More than 10 is 3 out of 36. And do they have anything in common? No, they don't. Right? They don't have anything in common. So 0. These are also mutually exclusive. So I just get 4 out of 36. I could do the same thing there. I'll save you a little time. I'll skip that one. Let's do this one to finish it off. Because cards are fun. A card is drawn from a standard deck of 52 cards. Find the odds in favor of drawing a heart. Then find the odds against drawing an ace. So, a card, we have one card here. In favor of drawing a heart. So, remember, if you remember from earlier, there's 13 hearts in a deck. There's 52 cards. So that's it. 1 out of 4. Odds of getting a heart. Now look at this one. This is what I want to do. So odds against drawing an ace. So there's 4 aces in a deck. But I don't want those 4 aces. I want against drawing an ace. What's the odds of not getting an ace? Well, there's 52 total. 52 minus the 4. 48. And there's 52 cards total. Right? If I want not an ace, or just not a value in general, I just do 1 minus getting an ace. We'll talk about that more later. But that's how you do not something. I want not an ace. You do 1 minus that. So I have 52 is my total. So I could have done 52 minus over 52 minus the odds of getting an ace, which would be 4 out of 52. Anyway, that's it.